Once we understand the joint mechanics, then we can optimize the joint strength. That's what we will see in Module 11, methods to increase the joint strength. We understand now the joint mechanics. We can now think about methods to increase the joint strength. That's what we are going to do in this module. So we understood that everything happens at the ends of the overlap. So if we could decrease the stress levels at these points, then of course we can increase the joint strength. This is what happens when you use a spew fillet. Here you have a joint where there is no spew fillet and the load transfer needs to go through everything through this tiny point, whereas when you use a spew fillet, then you have a smoother load transfer, and this will decrease the stress levels at the ends of the overlap. So you have this situation here, high stress at the ends of the overlap. If you put the fillet, then this decreases to here, and this increases the joint strength. The idea is always the same. You want to decrease locally the stiffness of the joint so that the stress will decrease. If the stiffness is lower, the stress will also be lower. You can do that with a spew fillet. You can also do that by changing the shape of the adherent and introducing a taper. It can be an external taper, an internal taper, or external taper plus spew fillet, which is even better. This can increase really 2-3 times the joint strength, especially if you talk about composite materials. With composite materials, with this situation, you might have a delamination. With this situation, it doesn't fail anymore in the composite, but fails somewhere here in the adhesive. And you can have really 2-3 times higher joint strengths. You can also use functionally graded joints. That's a very innovative method where you have an adhesive along the overlap which properties change. You can start with something simple if you want. You can use 2 adhesives. At the ends of the overlap you have a flexible adhesive that reduces the stress level and a stiff adhesive in the middle. But really what you want is an adhesive which properties vary gradually along the overlap. Something explained here. At the ends stiff, and as you go towards, at the ends flexible, and as you go towards the middle it gets stiffer and less ductile. And ideally you get a situation where you have a perfectly uniform stress distribution along the overlap. All right? There are various ways to do it. You can do it with non-uniform heating. You can do it with non-uniform mixing of particles. Already it's possible to do functionally graded joints. We know that we use a lot of composites in airplanes, but we need to be very careful with composites, as you know, because of the low transverse strength, the strength through the thickness. What can you do? Well, first of all, you can, or you need to make sure that the alignment of the fiber is the right way. You shouldn't put the fibers in this direction when you load the joint. It should be in this direction, which is represented in this slide here. What you can do also is reinforce the transverse strength of the composite. You can do a stitched composite or use Z-pins. It improves the strength in this direction, okay? But there is still another way you can do, which is using fiber metal laminates, okay? So it's along the width you are going to use different types of laminates to avoid delamination of the composite. You can do it locally, which is indicated here and here. There are some colleagues from Germany, DLR, that have done that. They surface toughen locally the composite so that it does not laminate. Here in Porto, what we have done is use a layer of metal all the way through the joint, as represented here. I think it's quite clear. You have on each top each face of the composite a layer of aluminium which delays the delamination in the composite, and like this you have a much higher joint strength. So that's methods that we have for composites. Finally, I want to mention a method that we can use when we have big temperature variations, which we have typically when you use supersonic aircraft, like the one indicated here. When we fly at 2 or 3 times the speed of sound, then with the friction of the air, the fuselage of the aircraft can go at very, very high temperatures. And you don't have adhesives that are top at high temperature and top at low temperature. You have adhesives that behave quite well at high temperatures. For example, you take a bismuth-amide, it's excellent at high temperature, but when you put it in a joint at low temperature, it's extremely brittle. So you would have something like this. On a graph, joint strength versus temperature from minus 65 to plus 100. On the other hand, you have adhesives that at low temperature are really, really great. That often epoxy, for example, or a polyurethane adhesive or a silicone adhesive at minus 55, it's fantastic adhesive. However, when you use it at 200 or 100, it doesn't have any strength, so it would have this type of behavior. So you don't have an adhesive which gives you a good compromise between low and high temperature. But what you can do is combine the two, as indicated here, or here. You put the low temperature adhesive at the ends of the overlap, and you put the high temperature adhesive in the middle of the overlap. When you are at low temperature, it's the low temperature adhesive that is at the ends of the overlap that works. When you are at high temperature, it's the opposite. It's the high temperature adhesive in the middle of the overlap that works. Of course, you will not, when you use a mixed adhesive joint, when you use the two together, you will be here. In other words, you will not be better than the low temperature adhesive alone at low temperature. And you will not be better than the high temperature adhesive alone at high temperature. But overall, you will have a better behavior. That's the objective. So that concludes this module. Again, we have seen various methods to improve, to optimize the joint strengths, all methods that are very obvious when you understand the joint mechanics.